Today we're going to talk about the addition of integers. I know in previous lessons we've talked about the rules for adding whole numbers and natural numbers, so we're going to add to that today and we're going to talk about the addition of integers. First of all, I would like to define what integers are. Integers is a subset of the real number system, and it contains all of the whole numbers and their opposites. Integers are whole numbers 0, 1, 2, 3, 4, 5, and etc., and all their opposites. So -1, -2, -3. And you can see from the drawing that I've presented here, it includes the positive integers, the negative integers, and 0. We represent the set of integers using the symbol of a capital Z. So I've included this in set builder notation that it includes all the numbers 0, 1, 2, 3, and its opposites, and etc. Integers does not include fractions, it does not include decimals. We're only talking about whole numbers and their opposites. A lot of times students will get confused when they do word problems. If we throw in the word integers, they don't exactly know what we're talking about. So by setting this foundation and teaching them what an integer is, it's going to help them in future math courses. When we talk about opposites, we think about opposites as being opposites in signs. Numbers are considered opposites on the number line when they're their exact distance from 0, except in opposite directions. Negative numbers are the opposite of positive numbers and vice versa. So an example of that would be 4 and -4 are opposites. -3 and +3 would be opposites. They're equidistant from each other on the number line in opposite directions. And so you'll spend a little time when you're talking about integers, especially because integers deal with the whole numbers and all of their opposites. You'll take a little bit of time when you're teaching this to teach students how to find the opposite of a number. So let's talk about the rules for adding integers. We'll start off with a simple rule, the addition of two positive integers. This is very simple. If we're going to add two positive integers, we're simply going to add the two numbers together and keep the positive sign. And so this is fairly easy for students if I'm adding an example like 4 plus 5. We know that 4 plus 5 are both positive. We add them and they stay positive. So typically students don't have a problem adding two positive integers. But let's talk about if we were adding two negative integers. An example would be -4 plus -5. The traditional method says that when I add two numbers together that are both negative, I'm simply going to add them and I keep the sign negative. This is where you're going to have to spend a little bit more time making sure they really grasp the concept of a negative plus negative equals a negative, because it's going to carry over into the future lessons when you start talking about a negative being multiplied by a negative being a positive number. And so students, especially early childhood education students at this level, really need to build a good foundation about knowing the difference when I'm adding two negatives and when I'm multiplying two negatives. The one that they typically may have a problem with or are going to struggle a little bit more with is when you're adding a positive or negative integer. The rule for that is we're going to subtract the largest number from the smallest number and keep the sign of the largest number. So I've written two examples out here for you. So we're going to start off with example 3A. Example 3A says -4 plus +5. You sort of disregard the signs and you're going to subtract the largest number, or take the largest number and subtract the smaller number. So I would go 5 minus 4, I'm going to get 1, and then determine the sign of the number. I look back and see which number was bigger. Since 5 is bigger, I carry its sign. So the answer to 3A would be +1. 3B, same scenario. This time I'm adding 4 plus -5. So I'm just going to subtract them, disregarding their signs. 5 minus 4 is 1, but this time, because 5 again is the bigger number, we carry the sign of that 5. So my answer would be -1. There are four integer algorithms that I want to talk about with addition. Chip model, the charged field model, the number line model, and the pattern model. All of these are good beginning algorithms to teach students how to add integers. So we're going to start off talking about the chip model. I like the chip model because it is a visual representation of the way that we add integers. So students typically can remember it very well. In the chip model, we're going to use colored chips to represent integers. And you can see in my example that I have chosen the yellow chip to represent a positive add-in, and I've chosen a red chip to represent a negative add-in. Now, as you're doing this, in order for us to be able to correctly teach students to add integers, they're going to have a good idea about how to make zero with these chips. They need to know for one positive, there's exactly one negative needed to make zero, and they're going to cancel each other out. So there are going to be times that we're going to use that idea of making zero to be able to add integers of different signs. So what we're going to do is we're going to determine the amount and the color of the remaining chips that are left, and we'll write the corresponding integer, carrying the sign. Whether if they're positive left, we'll carry a positive sign. If they're negatives, we will carry a negative. Let's look at an example of how the chip model works. This is example 4. We want to model the problem by drawing chips and then solving it. So our example says that we're going to take 4 and we're going to add -6 to it. So to represent the number positive 4, I have included 4 positive chips. I need to add 6 negative chips. And you can see that I've spaced it out. The reason that I've spaced it out is I have 6 negative chips, so I needed 6 red chips. Well, this positive is going to cancel out with that negative and make 0, and so forth. And so we will teach students that zero concept, and we're going to cancel them out, and that leaves me with 2 red chips. And since red chips represent negative, my answer will be -2. This gives students a really good idea about knowing the difference between the positive integers and the negative integers, and just seeing a visual representation of what does it really mean to add -6. Now, as you move up through the early childhood classes, you're going to want to put some good examples with this. When we're talking about positive and negative numbers, it's a good idea to use real-life examples, which we'll talk about, such as dealing with money. If I have $4 but I pay a $6 debt, or I need to pay a $6 debt, what does my bank account look like? So using real-world examples is a good way to get students to remember these rules. The charged field model is very similar to the chip model. It is also a visual representation of the addition of integers. It's very similar, again, to that chip model. The only difference, instead of using the charges, or instead of using the chips, we're going to use charges. And so instead of circles, I'm going to use pluses to represent the positives and negatives, charges to represent negative numbers. So we do it the same way. If I do 4 plus -6, you can see that I take 4 plus signs to represent the positive 4, 6 negative signs to represent the -6, and again, we go through teaching them about making zeros. We cancel them out until I can't cancel out anymore, and I'm left with 2 negative charges. So my answer, again, would be -2. Again, a good model because it's very visual. One of the important ones that we use, typically starting off teaching the addition of integers, is the number line model. This is, again, a visual representation. We want to make sure that we're addressing all types of learning styles. That's the reason that we teach these different algorithms. To do the number line model, we're going to use the number line to add integers. And the way that we do this is we're going to always start at the number 0. If our first number is negative, then we're going to move on the number line that many spaces to the left. If the number is positive, we're going to move that many spaces to the right. The distance between those two arrows is going to be the answer of our problem. And when you're looking at the distance, you're going to see on which side of 0 that number is. If you're on the left side of 0, your answer is going to be negative, and if you're on the right side, it's going to be positive. Very important that you emphasize about the correct sign. I've been teaching math for a lot of years, and of course, one of the main things students mess up on is their signs. They'll get the answer right, and they'll put the wrong sign. So it starts again with building that foundation. Here's an example of how we would actually use the number line model. We're going to go back to that same problem, 4 plus negative 6. So we're going to start at 0 on the number line, and since my number is positive 4, I'm going to move 4 units to the right. I'm going to add negative 6, so this is where I go back 6 units. So I count 6 units back. So here I am. I'm at the negative 2. You can see that that is the distance that number is from 0, and since it's on the left, our answer is going to be negative 2. Students typically like the number line model. They like being able to see it and count in which direction, and again, it's emphasizing the difference between those positive and negative integers. The next example that I want to talk about is the pattern model. The pattern model is exactly what it says. It uses patterns to establish sort of a rule that's going on, that we could finish it out. In order for the pattern model to be successful, students have to have a good concept of how to add the whole numbers. So that's going to be a skill that they need to know before they use this pattern model. They should be familiar with the whole number addition. So say I was trying to add something like 4 plus negative 2, and that was my problem. I've drawn a chart here, and I've tried to establish a pattern, and we see that our number 4 stays fixed. And I add 4 plus 3. Again, students would be very familiar with that. Whole number addition, my answer is 7. 4 plus 2, I get 6. 4 plus 1, I get 5. 4 plus 0, I get 4. So what's happening is my 4 stays the same, and I'm adding a number that is decreasing by 1. Well, if you look at what's happening, my sum is also decreasing by 1. So what I can do is I can carry that pattern forward. 4 plus negative 1, then I'm going to decrease by 4, by 1, and I get 3. 4 plus negative 2, I'm going to decrease that sum by 1, and I get 2. So they would be able to fill out, using a pattern, what the answer would be. Might be a good idea if we started off getting students an example where we had a table, maybe we had filled in what was in yellow, and then they finished filling out the ones that are in white, trying to find the pattern that's actually happening. When we talk about integers, we talk about starting with 0, our positive numbers on the right, our negative numbers on the left. We need to mention absolute value. Absolute value of a number, A, is written with A and the bars around it. That tells me that I'm taking the absolute value of A. When you're teaching absolute value, you just want to remind students that absolute value is the distance on the number line from 0 to A. You want to make a connection between absolute value being distance. When you make that connection, you're emphasizing that because absolute value talks about how it is the distance a number is from 0 on the number line, distance can never be negative. I may walk backwards to Walmart, but I've still walked the distance. Absolute value will always be positive or 0. So if I take the absolute value of positive 4, like in this example, how many units is 4 from 0 on the number line? It is 4 units. So the absolute value of 4 is 4. The absolute value of negative 4 is also 4, because negative 4 is also 4 units from 0 on the number line. So the absolute value of any number, whether it's positive or negative, will always be a positive answer. When I'm teaching this in class, I always say that absolute value is absolutely always positive or 0. We can't talk about adding integers without talking about some important properties of integer addition. So we're going to go over some properties. These properties are given that we have integers a, b, and c. The first property that I would like to talk about is the closure property of the addition of integers. The closure property applies when we're talking about two unique integers, a and b. All the closure property says is if I add two integers together, my sum will always be an integer. So if I take -3 and I add together a different unique integer, my answer will always be an integer. There's no way that I can add two integers and my answer come up to be a negative, not a negative, but my answer come up to be a decimal or a fraction. An integer plus an integer will always be an integer. That's what the closure property of addition means. We want to talk about the commutative property of addition, and we're going to start off talking about two terms. The commutative property of addition of integers is very similar to that of whole numbers. If I add two numbers together, it does not matter in what order that I add those numbers. It does not change. So an example here is if I add 4 plus 8, then I could flip those numbers around and swap it and add 8 plus 4. Either way that I add those two numbers, I'm always going to get 12. So one example that we could probably do with students to teach them the commutative property is to complete the statement. If 5 plus 7 equals, in order to complete it using the commutative property, we're just going to flip those numbers around. 7 plus 5 equals 12. I do want to make a note about the commutative property because in previous work that I've graded, some students are saying something that is really the commutative property and identifying it as an associative property just because it has three terms. I still can do the commutative property of the addition of integers with three terms. So I want to look at an example like that. If I had, say, -2 plus 4, and then I add 6 to it, my answer is not really what I'm trying to get at here. I want to rewrite that using the commutative property with three terms. In the commutative property, I'm going to just flip this around. So this will become 6 plus -2 plus 4. When you're looking at things that have three terms and you're trying to determine if it's commutative or associative, I really want you to look at the order of those terms. Look at this. In the first, or on the left side, I had -2 plus 4 in parentheses and I added 6 to it. If I look at the right side, the order of those numbers has changed. Now it's flipped around and I've got 6 plus -2 plus 4. If the order of those numbers have changed and it's just simply a flipping, then that represents the commutative property of the addition of integers. And we're talking about commutative property with three integers. Let's talk about the associative property. The associative property of the addition of integers deals with three terms just like I was talking about. But the associative property says that I simply can shift the parentheses, that changing the grouping of the add-ins, that shifting the parentheses does not change the sum. If I have a plus b plus c and I add a plus b together first and then add c, it's going to be the same thing if I go and I add b plus c. What I want to show you the difference between the associative property and the commutative property is that in the associative property, the order of those numbers does not change. I have A, B, and C. In the second example, I also have A, B, and C. The only thing that I've done is I've shifted the parentheses. So when you're trying to determine with three terms if something is associative or commutative, look at the order of those numbers. Example 8, I have 5 plus 6 plus 2. If I was trying to rewrite that with the associative property of the addition of integers, I would write the numbers in the same order, 5 plus 6 plus 2, and I would simply shift the parentheses. We see that 11 plus 2 gives me 13, just like 5 plus 8 gives me 13. So simply shifting the parentheses does not change my answer. Another example, if I wanted to take 4 plus 7 plus 3 and rewrite it as using the associative property, the order of the numbers does not change. 4 plus 7 plus 3, I simply shift the parentheses. The identity property of addition follows the same suit as whether we're talking about whole numbers or integers. 0 is just a unique integer that for all integers, if I add 0 to that integer, I always get that integer. So adding 0 to an integer does not change it. For example, if I take 0 and I add to 6, I get 6. If I take 0 and I add to negative 6, my answer is negative 6. The identity property of addition. When I add 0 to it, its identity does not change. When we talk about the additive inverse, we're really talking about the opposite of a number. By definition, the additive inverse property of integers states that for every integer, there exists a unique integer that is the opposite, which we call its additive inverse. And the additive inverse property says when I take a number plus its additive inverse, I always get 0. If I take a number plus its additive inverse or its opposite in sign, I always get 0. An example being if I take 7 and I add negative 7 to it, I get 0. If I take negative 7 and I add the opposite of that, which is positive 7 or its additive inverse, I always get 0. So you need to know that when you take a number and add its additive inverse, you always get 0.